I want to introduce a new technical term because remember our plan is to take all of these vague words about feedback and modeling and turn them into definite mathematically defined concepts. And one of the most important ones, and a concept that we're going to be using again and again and again through the entire course and 30B also, is the concept of a function. And so the question is, what are functions? We've been talking using concepts like phrases like depends on, the force of friction depends on velocity, or we draw a graph that shows the dependence of the force of friction on velocity. We also said things like the change in the shark population depends on the tuna population. And indeed, in the very concept of what a model was, we said a model is a statement like this where x prime, the change in x, depends on x and y, and y prime depends on the change in y, depends on x and y. So what we need to do now is we need to lose this vague concept of depends on, and we need to replace it with a more rigorous concept, which is the concept of a function. Now, maybe you think you already know what a function is. We did functions in high school. Oh yeah, x squared. X squared is a function. That's a function. But be careful. Don't confuse function with formula, because there are functions that aren't formulas. You're going to see a couple right now. There are functions that aren't formulas, and there are formulas that aren't functions. For the example of the latter, y equals square root of x is not a function. We'll talk about why. So what is a function? In the most general mathematical setting, the way to define a function is you need the following configuration. Number one, you need a set x, which we're going to call the domain of the function. You're going to need another set y, which we are going to call the codomain of the function. And then the function itself is going to be an assignment of elements of y to elements of x. Every member of x gets assigned an element of y. And so this concept of assignment of every x gets assigned a y, that is the essence of what a function is. So it does not have anything to do with formulas or numbers, as we were saying. Here's a very basic example. So our set x, our domain, is going to have four elements. The letter A, the letter M, the number 22, and a picture of a dinosaur. That's the set A. And that's just to stress that this can be a very arbitrary set. Our codomain is going to be another set. This set has 5 elements, and those elements are candy cane, the number 6, the number 22, the ace of clubs, and the letter S. That's our codomain. And then I'm going to define a function f that is going to assign elements of the codomain to every element of the domain. And here it is. So the letter A gets assigned the number 22. The letter M gets assigned candy cane. The number 22 gets assigned a letter S, and the dinosaur gets assigned the letter 22. Notice that both A and the dinosaur get assigned 22. Is there anything wrong with that? No. Perfectly okay for many elements in the domain to be sent to this assigned the same element in the codomain. That's cool. That's admissible for a function. As a matter of fact, an extreme case in which every element of the domain is assigned the same element of the codomain, that's perfectly okay. And those are functions. So what is not a function? Here is not a function, and it's not a function because the letter M in the domain does not get an assignment. The other three do, but M is not assigned anything. It is therefore not a function. Here's another not a function. Now, the problem is not a failure of assignment. Now we have too many assignments. The number 22 is assigned both the candy cane and the letter S. That's impermissible. That is not a function. The essence of a function is that every element of the domain gets assigned exactly one element of the codomain, never none and never two, exactly one. So just some language and terminology that we use when we talk about functions. In this configuration, we have this function f, and you see it is taking dinosaur and assigning it the number 6. We are going to state that fact with the language as written there, which we will read out loud as f of dinosaur equals 6, or we will write it in that way, f parenthesis dinosaur equals 6. Those two mean the same thing. One is the reading of the other. And in general, we're always going to be saying that y equals f of x, where y is an element of the set big Y and little x is an element of the set big X. So this is our standard language, y equals f of x. Now, when we look at what f does to the sets, we're just talking about what f does to the elements of the sets, f of dinosaur equals 6. Now we're talking about what f does to the sets themselves, and we will say that the function f takes x to y. And that's just a language that we use. F, the function, takes x to y. We will also say f takes x to y for a little x and a little y, where little x is an element of big X, little y is an element of big Y. We're also going to say f takes x to y. So for example, f takes dinosaur to 6 is the correct language to talk about this situation. Now functions, when functions are functions of numbers, they can often be represented by graphs. And here is a function. The black curve is showing y as a function of x. And the key test that it is a function is we take any value of x. Remember, f is taking here, f is the black curve, and it's taking the set x to the set y. And the key here is that, again, exactly 1y for every x. So if we pick any element of x and shoot a straight line up, it should intersect this graph of the function exactly once. And in this case, you see that that happens. Every x gets exactly 1y, and so the black curve is a function. Now, that exactly 1y for every x, that can be violated, and then you get non-functions. So for example, here is not a function, as you would see from its graph, because here are x values that do not get a y value. And so this is not a function. And then the other way you can fail to be a function is right here. This is also not a function. Why? Because this x gets 2 y's. So that's also not a function. So that's the general rigorous concept of a function. You can really think of it as an input-output machine. You input an element of the domain, and it outputs an element of the codomain. And so in that sense, it's like an input-output machine. So for example, here's a super simple case where this function f is a color switching function. It takes as an input the red star and gives an output of the blue star, and it takes as an input the blue star, and it gives as an output the red star. So if we wanted to take that machine and write it in the language that we've been using for functions here, it would look exactly like this. The two sets x and y consist of the red star and the blue star. And it doesn't really matter which order they're in. We could have put them both in the same order. The set y is also the red star and the blue star. And the function f assigns to the red star the blue star and assigns to the blue star the red star. So this representation of a function on sets is equivalent to writing the function this way as an input-output machine. Now there's one cool thing that we have to be able to do with functions, and that is combine them, chain them one to another. So let's talk about that process, which is called the composition of functions. Suppose we have two functions, function g and a function f. G has as its domain the set x and has as its codomain the set y. F has as its domain the set y and as its codomain the set z. When you have this, you can then define a new function h. And that new function h is going to take x to z. And h is defined as f of g of x. So h of x is f of g of x. We can now write the configuration in this way. Here's g taking x to y. Here's f taking y to z. And now f of g, which is the function h, is going to take x to z. And that's written f circle g. It's read the composition of f and g, or you can say f of g. Just don't say f times g, because that circle does not mean times. It means the composition of functions f of g. So this new function, f composed with g, or f of g, takes us from the set x to the set z. So just a test here to see if we can understand this concept of chaining. Here are two functions, f and g, and they're very simple. F is defined on the set whose elements are the number 3 and the number 4, and f of 3 is 5, and f of 4 is 6. And the set g, the function g, is defined on the set 3, 4, and gives you 2 as an output and 3 as an output of the input 4. And my question is, can these two functions be chained in either order? Can we write f circle g? Can we write g circle f? Here's another function. We've changed it a little bit. Now, the function f takes as an input the number 3 or the number 2, and f of 3 is 5, f of 2 is 6. G of 3 is 2, and g of 4 is 3. And now we ask again, can we chain these two functions? Can we write f composed with g? Can we write g composed with f? Finally, I want to do one more homespun everyday example of function composition. First of all, let's take as our function g an ordinary restaurant menu. Yeah, a menu is a function from dishes into prices. And for every dish, you get a price. There are no unpriced dishes, and there are no dishes that have two prices. So a typical menu is a function from dishes, in this case, from hot beverages, into prices, which are, of course, net prices. And by net, I mean not including tax. Now, the tax rate is another function with a different domain and a different codomain. The domain here was beverages, hot beverages, and the codomain was prices. And here, the domain is prices, and the codomain is gross prices or after-tax prices. And so the function f, which is the tax rate, takes net prices into after-tax prices. As a matter of fact, there's even a formula for this function, although not for this one. There's a formula for this function, which is z equals 1.08y, because we live in a county in which there is 8% sales tax. So the function there can actually be written out as a formula, which will sometimes be the case, but as you see, not always. So then we can take these two functions and we can indeed compose them into f of g, and f of g takes x to z, which takes hot beverages to after-tax prices. So that's an example of a successful composition. And the composition of the use of the notion of function is going to be extremely important. Models are functions. The changes are functions of the state variables. And functions are going to be super important for us in everything we do. And the composition of functions is also going to be playing a big role. So that's a critical concept that we can now define rigorously. A function is an assignment of exactly one element of the codomain to every element of the domain.